Principal component analysis is a technique used in machine learning to reduce dimension. In this video, we are going to look at what it is, we'll write some Python code, and in the end, there will be an interesting exercise for you to work on. Let's say you're working on building a machine learning model to predict property prices. Here, all the columns on the left-hand side are the features or the attributes of the property that decides the price. So the column in green is actually your target variable. You probably already know that the price of the home is mainly dependent on area, which town it is in, plot, etc. It depends on how many bathrooms you have in a property, but not as much. For example, 2600 square foot home with 2 bathroom versus 3 bathroom, price won't be that different. But if you go from 2600 to 3000 square feet, price will be significantly different. So clearly area, plot plays a more important role in determining the last price. Bathroom plays a little bit of a role. And how about this particular column, trees nearby? Whether you have 2 trees nearby your home or 3 trees nearby your home, you don't care that much. So that column probably doesn't impact the last price at all, or it impacts it only a little bit. When you're solving real life machine learning problems, you will have many columns, 100, 1000, 2000 columns or features, and you need to do something to identify the features which are very important. You're working on, let's say, handwritten digit classification, where you have digits which are written by hand, and then you try to classify as one of the numbers from 0 to 9. Here, this image is represented as pixel. Let's say this is a grid of 8 by 8, and every number presents the color. So 0 means black, 16 means highest white, And since it's an 8 by 8 grid, there are total 64 pixels or numbers that helps you determine what number it is. So these 64 pixels are called features. And if you represent, now if you think about some of the pixels in these images, you will find that those pixels don't play any role at all in figuring what digit is it. For example, these 2 pixels here, or pretty much any pixel in this last column, no matter what number it is, these pixels are always black. So we can say that these pixels are not important feature. And what if we get rid of these features? We get 2 benefits out of that. First, the training is faster. Machine learning training takes a lot of time, a lot of compute resources. So you want to save the training, you want to make it a little lightweight, and your inference can also be faster. And data visualization becomes easier. Let's say you have 100 features and somehow you reduce those 100 features into only 2 features or 3 features. Then as a human, you can plot it on a 2D or 3D graph. You can visualize it, and data visualization helps you a lot in terms of your final decision making with regards to what kind of model you want to build. PCA is a process of figuring out the most important features or the principal component that has a maximum impact on a target variable. PCA will create, in fact, the new feature called principal component, PC1, PC2, and so on. So again, going back to the digits example, let's say I have 64 features. Out of that, I am plotting only 2 features, corner pixel and a central pixel. Now here, these clusters represent different digits. You immediately notice that the corner pixel is not playing an important role. Maximum variation is on the y-axis, or maximum variance is on the y-axis, which is a central pixel. So if I ask you to reduce this 2 dimension into 1 dimension, you can easily do so by getting rid of corner pixel. So this graph that I have drawn on the right hand side, it is 1 dimension. I mean, I know the graph is not perfect, it still looks like 2 dimension, but you get my point. To reduce this from 2 dimension to 1 dimension is easier. Let's look at the iris flower dataset, where sepal width and sepal height determine what kind of flower it is. If you have a scatter plot like this, you can draw a line which covers the maximum variance. So this line covers the maximum variance or the maximum information in terms of features. And you can draw a perpendicular line which covers the second most variance, and these are called principal component. So here PC1 is this axis which covers the most of the variance. PC2 is the axis that covers the second most variance. So when you apply PCA, you get a chart like this. And I know I have done only this graph for 2 dimension, but really if you have 100 dimension and if you apply PCA, you can figure out, let's say, 10 most important principal components. So for 100 features, you can actually create 100 principal components in the descending order of their impact on the target variable. So for digits, if I have to load this in a data frame, pandas data frame will look like this. There's a little error, it's like pixel 63 because I start with pixel 0. But you already see pixel 0 and 1 has all values is 0. They are not kind of important. So when you use sklearn library and call PCA method where you say, okay, n components is 6, you're basically asking PCA to extract the 6th most important component. And that will look something like this. So what this is doing is calculating new features, and these features are such that PC1 covers the most variance in terms of features, in terms of information extraction from your dataset. PC2 is the second most highest component that contains a lot of information about the features of your dataset. Here I give 6. You can give it anything. You can have 2, 3, 4, 5, trial and error. You can also give a different parameter to this method, which will be like 0.95, which means, get me 95% of information in terms of features, get me 95% of variance. So you can do that. We'll see that in the actual coding section. But few things to keep in mind before using PCA is you need to scale the features, because if you don't scale it, it's not gonna work. Okay, for example, here is a chart, and if this graph is in millions and this graph is in a normal value, the graph might become skewed, and the PCA will not work as per your expectation. Accuracy might drop. So it's a trade-off when you're trying to reduce. Let's say you have 100 features, and if all 100 features are important and they're trying to contribute to end target variable, if you reduce from 100 to 5, you're going to lose a lot of information. So we'll see all of that in the coding session. But just to summarize, PC is called a dimensionality reduction technique as it helps us reduce dimension. We already saw here, in this case, we had 64 dimension. This helped us to get to 6 dimension. And when you have less columns, your computation becomes much faster. And it also helps you to address the dimensionality curse problem. In machine learning, dimensionality curse is a big problem. So many data sets having so many columns, so many dimensions, and that makes our model really complex, hard to visualize. And PCA is an excellent technique that help you deal with dimensionality curse. Let's get to Python coding now. I opened my Jupyter notebook and imported some important libraries. I'm going to use the handwritten digits dataset from sklearn dataset module. Let's load the dataset by calling load digits function. And when you do that, it loads the dataset, and you can call dataset.keys to get an idea on what the dataset is all about. You can see that dataset.data will contain all the pixels, and these are the feature names, and this is the target array. Right now, let's look at dataset.data.shape. So there are 17, almost 1700 or 1800 samples. Every sample has 64 columns. So if you look at the first sample, it's a flat one-dimensional array of 64 pixels. And if you want to visualize this data using matplotlib library, you need to convert it into two-dimensional array. And the way you do that is by calling reshape function, because this is numpy array. And when you do 8 by 8, it just converts one-dimensional array into two-dimensional array of pixels. Now you can import matplotlib and use the plot. I'm gonna just plot a gray image, and when you do plot dot mat show, like metric show, it will show that it will show a picture of that array. What is my array? This is my array, right? See, two-dimensional array. So I'm gonna just put Control C, Control V, and my first digit looks like this. This is clearly 0. If I look at my second data sample, see, it is 1, then 2, and so on. Like 50th sample will be, I think this is 2. Okay, so this is how you visualize it. Now let's look at the target. When you do dataset.target, it's a huge array, but it is your end class. If you do unique, you will find the way you do unique is by calling np.unique, and you see the numbers are between range 0 to 9. We already saw, let's say our 8 number here is, which number it is? Okay, I can check it here. So if you do 8, this is the 8 number. I know it looks weird, but let's do the 10th number. So 10 number is 9. See, 9. So this dataset.data is your feature, and dataset.target is your class. Basically, we are classifying this in 10 classes, 0 to 9. Okay, let me create a data frame now. So I can do pd.data frame and just supply dataset.data here, and that will create a data frame for you. But the column headers are randomly assigned, so I'm going to do columns. You can say dataset dot feature names, and the feature names are all the pixels, like 0th row 0 pixel, 0th row first pixel, and so on. And I will just save that into a data frame object. Okay, my data frame object is ready. Now I know from this data set the values are between 0 to 16, but if you want to confirm, you can do df dot describe. And for each of the columns, if you look at min and max, this column is useless, but if you look at min and max for most of the good pixels, it will be between 0 and 16. Okay, so 0th is my minimum value, 16 is my highest value. Now I'm going to store this in x and y. So df is my x, and my y is my target set. So again, what is my x? X is my data frame. What is my y? Is my target classes, the digit which tells you 0 to 9. Now I would like to scale these features before building my machine learning model. So I'm just going to use the standard scaler. Scaling is a common thing that I do before training my model. And sklearn provides very convenient API to do that. When you do scalar.fit transform, it will just scale that x thing, and you can store this into x scale. So when you print now x scale, you will see the values are their scale using the standard scalar. I think -1 to 1. You can use min-max scaler as well. Okay, now we are ready to train the model. So we are going to do our usual thing, which is train test split. You already know this by this point, and I'm going to call train test split on my X scale. So X scale and Y, and I will keep my test size to be 20%. You can do 30%, whatever. And I'm just keeping random state for reproducibility. If you don't want to keep it, it's fine. And in the result, what I get is X train, X test, Y train, Y test. This should be in your muscle memory, friends, if you're doing machine learning for some time. Now, I am ready to train my model. Well, I'm going to use logistic regression. You can use random forest, decision tree. There are so many classification techniques, but I'll start with logistic regression. I will create a model, which is an object of this class, and then model.fit. Again, pretty standard. And model.score. So I do model.score to measure the accuracy. 97%. See, this is pretty amazing. I get 97% accuracy by training on all these features. But now let's do PCA. So to do PCA, you can import PCA from sklearn decomposition, and then I will create a PCA variable. So let me increase my font size. It's very simple, PCA, and here you supply two type of arguments. You can either say how many components you want. You can say 2, 5, trial and error, you can figure it out. But what I'm going to do is I'm going to supply 0.95. What this will tell PCA is that retain 95% of useful features and then create new dimensions. You're not explicitly saying I want only 2-dimensional as an output. You're saying give me retain 95% of information, retain 95% variation, and then whatever features you come up with, I'm happy with that. And then PCA.fit transform. The API is quite simple. You supply your data frame here, you get a new data frame with new feature, new principal components, and when you do xpca.shape, see, now you got only 29 columns. If you look at your original data frame, you had 64 columns. So 64 columns to 29, it probably got rid of unnecessary things such as this guy, for example. See, 0th pixel, all values are 0. See, look at here. This feature is not needed at all. So it probably got rid of that, and it did not, by the way, just to make it clear, it's not like it will pick 29 columns out of it. It will calculate new columns. Okay. So if you do X PCA, you see, it actually calculated new columns for you. And if you do PCA variable dot explained variance ratio, it will tell you that my first column is capturing 14% of variation or 14% of useful information from my dataset. PC2 second component is capturing 13% of information, and so on. So this is how you print explain variation ratio. There is another thing called n components. It will tell you how many components you got, which is basically your columns, 29. So here PCA helped me reduce my columns from 64 to 29. All these 29 columns are computed column. They are the new feature. But good news is you can now use this new data frame to train your model. So I'm going to do train test split once again, but this time I will supply xpca, y remains for high, then my test size is 0.2, and I'll just keep my random state to be this. And as a result, what you get is your train and test data sets. And I'm going to use again same linear regression, logistic regression, sorry. And I will say logistic regression. This time I will fit on PCA and then model dot score and y test. Say I got pretty good accuracy, 97%, but let's say this failed to converge because total number of iteration limit reached. So I need to supply some maximum iteration. So I will say max iter. So I need to increase my iteration basically to uh, so that the gradient descent can converge. See, almost same accuracy. So you are realizing that despite dropping a lot of features, my accuracy is almost same. Here is 97.22, here is 96.994. So it's almost similar. Okay. Now you can create PCA by supplying the components explicitly. So I can say, okay, PCA, let's say my number of components is 2. Now this is what is going to happen when you explicitly say my components are 2. So I'm going to do PCA transform with my x PCA dot shape. Now we are telling that we want 2 components. Okay, so it will identify the 2 most important features, but here, see, let me see. So see, every data point is just 2 features. Now did it capture enough information? We are not sure. When you print explain variance ratio, you are capturing 14% and 30%, around 27-28% information. So naturally, when you use this data set to train your model, the accuracy is going to be low. So I'm just going to like same code, but I'm using the new PCA and the new data frame. And when you train the model, you see the accuracy is reduced to 60.83. So you take a hit, but the benefit you got here is your features are only 2. So your computation can be very fast. So you can decide what accuracy do you want, and then you can reduce your dimensions accordingly. So that's all I had for this video. Now let's move on to the most important part of this tutorial, which is an exercise. I'm going to provide a link of this exercise below, but it's very important, friends, that you work on exercise. And I have given a very good exercise. There is a data set which you can download from Kaggle, or you can see if you click on here, there is this heart CSV. And so there is a data set for heart disease, and using this data set, you need to predict if the person has heart disease or not, and you're going to use PCA. So work on all these 6 aspects of the exercise and let me know how it goes in the comment. Post below your solution, your GitHub link, whatever. And if you have any question, post in a comment below. And if you like this video, share it with your friends, so that they can learn. Everything is for free, friends. Exercise, explanation, all my YouTube videos are free, so you can have a learning at at almost no cost. So please share it with your friends and give it a thumbs up if you like this. Thank you.